Well, this will be a short video just to define what strong induction is, and then in future videos we'll do some examples. Remember that regular induction, or you may call it weak induction, just says that if you got a proposition that's defined for all natural numbers, proposition 1, proposition 2, proposition 3, ... to infinity, and you're able to prove that P1 is true, and that for some k, some natural number k, if pk is true, then pk plus 1 is true, you just proved all of those infinite numbers of propositions are true. Proposition 1, proposition 2, proposition 3, ... Well, strong induction is slightly different. We're going to take two integers, m and n, and we're going to define Pn, proposition n, to be a statement for all n greater than or equal to m. So m doesn't have to be the number 1. Okay, it could be, the statements could start at 3, proposition 3, 4, 5, ... or -3, proposition -3, proposition -2, -1, 0, ... If Pm, which m is the smallest, m we could say is the very first proposition defined, Pm, and if we can show that if all of these are true, we can prove that this one is true, then we proved that Pn is true for Pn is true. Where did I get Z? This should be K. Then Pn is true for all K. This one needs to be M. Sorry about that. Applies Pk. If this is true for all K, then Pn is true for all values of n starting with M. So just real simple, if M is equal to 4. The first thing we would do is prove the base case, if we were doing a proof by strong induction. Then we would prove, we would say that if we can show that if we assume that all of these are true from Pm all the way up to Pk, and we're able to prove then that Pk plus 1 is true, then we're done. So if M is 4, then what we have is a bunch of statements like this. So our base case would be, well, we'll see in a minute when we do an example. But what we need to prove, we for sure have to prove this as a base case. We might have to prove more, but we'll see that in another video. But if we show that for all values of k, if I assume P4 through Pk are all true, assume that, and prove Pk plus 1 is true, then we're done. So let me give you just one example where proof by induction would be difficult. I think we all know that every natural number could be written as a product of primes. The number 12 can be written like 2 times 2 times 3, a product of primes, uniquely. I mean, you could reorder them, but I consider that the same factorization. The number 19 is a prime number, so it's just 19. You think of that as a product of just one number. So let's suppose that using induction, I want to prove that 30 can be written as a product of primes. If I knew for a fact that 29 could be written as a product of primes, which it can, does that in any way help me determine that 30 could be written as a product of primes? It doesn't. Knowing all that information about 29 does not help me at all with 30. But if you told me that all of the numbers from 1 to 29 could be factored as product of primes, that helps me. Because now if I know all the way up to 29 is good, The number 30 is just what? Pick any two things. 10 times 3. The number 10 can be written as a product of primes. The number 3 can be written as a product of primes. And 30 is just 10 times 3. So take those two sets of products of primes and put them together, and you have the prime factorization of the number 30. So that's a case where regular or weak induction would not help you at all, but strong induction would help you immensely. So we'll do a couple of strong induction examples in the videos to come.